Welcome to the final session for the day on platinum deposits. And we will start with Cesar Ferreira Filho, who is also online in the spiritual realm listening in. So he will be available for questions at the end. He has confirmed, so we will see what happens here.
Hello, everyone, and good afternoon for those at Cardiff right now. My talk today is about some results we obtained in a project together with geologists from Bravo Exploration Mine and together with Eduardo Mansur in the Luanga PGE nickel deposit. I'm going to do is a brief overview of the geological setting, and then review some of the knowledge we actually have now about the Luanga complex. And then the important thing is show you some of the new features recently discovered in the Luanga complex, the new PGE nickel horizons. And then discuss some of the implications for the origin of the mineralizations in the Luanga complex. I'm not going to talk about the geology of the Carajás province. Important thing that is associated with a large igneous province, new Proterozoic, at the Amazonian crater. So this is very old terrains, and that's characterized by a huge cluster of layered intrusions. And these layered intrusions, they host several nickel deposits, that's including nickel associated with laterites, nickel in magmatic system, and hydrothermal system like the Jaguar deposit. So there is altogether, there's more than 6 million tons of contained nickel within this belt of layered intrusions. The Jaguar deposit is particularly important because some of the features that we are now recognizing in the Luanga complex, and especially the association or similarities with hydrothermal system that form IOCG deposit in Carajás, are the same that we have been describing at the Jaguar deposit. So the Luanga, what we call the Luanga PGE nickel deposit, was a deposit discovered by Vale, the exploration program 2003-2007. These are the resources that we right now we know. And then this geological framework, has been used in the previous descriptions of the Luanga complex. So there are now several papers that were published together with Eduardo Mansur in the Luanga complex, focus on different aspects of the Luanga complex and PGE nickel mineralization, but that's using the framework developed by Vale during the exploration programs. We are now in a new phase, trying to figure out all the new results from the new exploration program that's being developed. We actually impact what we already know about the Luanga complex. So in terms of, briefly, in terms of the geology and magmatic structures, a very typical layer, medium-sized layer intrusion with ultramafic zone, a transition zone, mafic large, upper mafic zone, steep dipping layers. And the Luanga complex, essentially this zone here located in the contact of ultramafic zone and mafic zone. So the PGE deposit, when we call the PGE deposit, they were saying it's essentially disseminated sulfides, relatively thick, 10 to 50 meter thick, strata-bound zone of disseminated sulfide, 1-5% sulfides, located right at the contact. There are several other horizons. I'm not talking about them associated with chromatites, associated with low sulfur high-PGE zones. But the deposit itself is this, what we call the main sulfide zone, or the sulfide zone, at the contact between the ultramafic zone and the transition zone. This zone here, the sulfide zone, is a very typical PGE deposit associated with base metal sulfides. One of the characteristics is very rich in pentlandite, a similar amount of pentlandite and pyrrhotite and minor amounts of chalcopyrite. And review the data that has come out from the new exploration data from Bravo, So several of the important features that we have described in the Luanga complex, they are supported by the new data. These include the high nickel tenors, so nickel on sulfur indicate very high nickel tenors, and high nickel copper ratios to platinum palladiums are usually below to 0.5 with a very good correlation between platinum and palladium. And there is a poor correlation with PGEs and sulfur, and this is possibly related with the alteration of the sulfides. We are trying to ask some additional questions. One is always the variability of this mineralization along the stratigraphy and across the stratigraphy of the complex, and also how this alteration that is widespread in the Luanga complex affect the sulfide mineralization, or the primary features of the sulfide mineralization. Looking now at some of these new discoveries. So one discovery, sulfide-rich zones located below the main sulfide zone within the ultramafic zone, and this has been called the Ni-Cu-Rhodium sulfide horizon, with some very good intersections in terms of PGE and nickel contents. So in terms of the stratigraphic location, that's close to the main sulfide zone, but located at the ultramafic zone, so below the ultramafic zone. And one feature that's much richer in sulfide than the main sulfide zone. Very typical magmatic sulfides, interstitial to silicates, olivine, and pyroxenes, consisting mainly of pyrrhotite, pentlandite, and minor chalcopyrite, and also partially altered to magnetite. So that's a later magnetite originated by alteration. We don't have the sulfide contents for these rocks yet, but we know that they have much more sulfur and less PGEs, so the tenor in terms of PGE tenor are much lower than the PGE tenor of the main sulfide zone. If we compare some of the chemical characteristics of the main sulfide zone and the nickel-rhodium zone, you can see that the nickel-rhodium zone has much lower platinum palladium contents, and also they have higher rhodium to palladium, higher rhodium content, and also they have much more sulfides, and also will have much higher sulfur compared to the 0.4 here, 0.5, so much higher sulfur than the main sulfide zone. The other important discoveries are some massive sulfides. They are located in the northern segment of the Luanga deposit, the Luanga complex, and they are associated with the lower portion. So some very significant intersections with high PGE, high nickel, high copper content, and this has not been reported on previous investigations of the Luanga complex. One surprise is that the host rocks are not primary igneous rocks, don't preserve primary textures and minerals, and they are essentially formed by hydrothermal rocks. So rocks are essentially amphibolitites with lots of magnetite, some garnet, some are banded magnetites and amphibolitites. So, and these rocks have the same characteristics that occur in hydrothermal rocks associated with IOCG systems in Carajás. Close by, especially in the massive sulfide, we have some partially preserved orthoperoxenites and norites. The sulfides are essentially pyrrhotite with associated pentlandite, so that's 89% is pyrrhotite with pentlandite, and variable amounts of copper include some copper-rich zone. The sulfides are intergrowth with hydrothermal silicates, so this picture here of sulfides intergrowth with amphiboles, so we don't have, and also some zones enriched in magnetite. In terms of composition, so the most PGE-rich samples are those of massive sulfides. You have some interlayer sample with less sulfides, with much lower contents. And usually the correlation of the metals are not very good, except for nickel, palladium, and nickel copper. So these include one very nickel copper rich zone, up to 10% copper. And we don't have Right here, if you look here, nickel copper, you can see very poor correlation in terms of nickel copper, platinum, palladium, also very poor correlation. We don't have sulfur content yet, but if you look at the massive samples, the massive sample will suggest a moderate nickel and copper tenors, 3% nickel, 0.5% copper. And relatively, that's compared with mesulfite zone, lower palladium and platinum in the range of a few ppm. Our interpretation of the massive sulfides, that they are not primary magmatic sulfide, they are hydrothermal, they result from the hydrothermal remobilization, possibly of magmatic sulfides from the Luanga complex. Comparing now three of these horizons, three of these mineralizations in the Luanga complex, the mesulfide zone, the nickel rhodium zone, and the massive sulfides, you can see that they have different metal contents, with the nickel rhodium being characterized by higher rhodium contents, and the massive sulfides we interpret as hydrothermal with a lot of scattering in terms of the results of platinum and palladium. So in terms of closing remarks, so we now recognize the different style of mineralizations in the Luanga complex that include both different type of magmatic, but also hydrothermal nickel sulfides. And the characteristics of the alteration zones associated with these hydrothermal sulfides are similar to IOCG type deposits in Carajás. So the alteration zones observed as in IOCG type deposit in Carajás, and also similar with those associated with the hydrothermal nickel. So we think that we may have here a good case study to investigate the whole metal from magmatic sulfide system are remobilized to form a hydrothermal nickel. Thank you, and I think it will be available for some questions.
Okay. I believe he is available for questions. So does anybody have any? Sure.
So, can you hear me? I was wondering, IOCG deposits, of course, you know, many people feel they come from a mafic source at depth. Is there any data on IOCG deposits in terms of PGE contents? We know they're gold rich, of course, but may they also contain PGE in some cases?
Hi, Wolf. In the Carajás region, so the PGE content of most of the IOCG deposits are quite low, and also one interesting thing that it is also low. The content of PGE, the PGE contents are also low in the hydrothermal nickel deposits. Are you guys listening to me?
Well, thank you very much, Cesar. We're going to move on to our next talk.
Okay.
Okay, we're going to stay in the Southern Hemisphere and get rid of that. Martin Clausen will take over.
Thank you, Steve. And let me just see if I can get this. Oh, aren't you supposed to? Okay. Well, it probably won't go down. White options. There we go. Okay. Hello. I'm gonna go right out into it about this potential PG deposit. It's not really a deposit yet, but we'll see. It is located in the Ni-Cu and orogeny in southern part of Namibia, or goes down through there, is an orogeny between the Kalahari Craton to the northeast and some Paleoproterozoic sort of microcontinents that probably were Paleoproterozoic magmatic arcs, the Richtersveld and Bushmannerland. Then you have the Kakamas, Narachap, and these, which is basically an origin. And it's not a real origin in that sense of a thickened crust. It has very high thermobaric ratios, and very much like other Grenvillian orogenies, which have recently been interpreted as back arc settings rather, right? To explain the high thermobaric ratios and the very low angle thrusting and thin crust. And such a setting is very favorable to generate mafic magmatism because you have a stenosphere very high up to decompression or melt. And there's actually evidence of this mafic magmatism in this setting. And because it's like a back arc setting, you can have slab push and pull, where you can get extension where magmatism comes up, and you have compression where magmatism is piling underneath the crust and getting ready to rise up. And we actually have 3 such mafic events during this very short, relatively short orogeny, 1.2 to 1 billion years. And the youngest of these actually copper mineralized is O'Keefe, if anybody knows O'Keefe copper district, which is generated by mafic magmatism. And then there is a 1.1 Umkondo event, which also occurs here, but also extends across the Kalahari Craton. It's surprisingly not mineralized. And then we have the mineralization that I'm gonna, so O'Keefe is roughly around there. And then we have the Kum suite we talk here is about 1215. So we had these mafic events about every 100 million years inside this setting, in accordion type tectonic setting we have here. This Kum suite has got these mafic intrusions here. Maybe I should look at this instead of rather than look up on the screen. It's composed of these complexes here that we see. And well, it's not really moving. Oh, okay. Anyway, this area is cut through by very spectacular, I'm sure you can see it on Google Earth, the Puff-Adder shear zone, a dextral shear zone with quite about at least 40 kilometers of displacement, which has sort of fragmented the intrusion there. And the TBC that we're going to focus on there, the Tantalite Valley Complex, has these shadow zones inside this deformation here, very spectacular. And this is where pegmatites come up very late, so this shear zone very late, about 1 billion years ago. In these shadow zones, these pegmatites come up, and those are the ones that are tantalite enriched and give the name to the complex, but we're not going to focus on that. Instead, we're looking at these mafic intrusions that are available major element bulk rock chemistry, and we can see that quite a lot of these are cumulate rocks, indicated if you with more or less plagioclase down in the yellow square, and mostly olivines, as well as some orthopyroxenes. So you can have some locogabbroic cumulates, and then you can have some more melagogabbroic to ultramafic cumulate as well. And then you have magmas that are not cumulates, that's in the melt area that are indicated there. And if we look at the which rock samples are cumulates, it's predominantly from the TBC. There are some 2 ultramafic samples from the sand fontaine, whereas there's very few cumulate rocks from the Kaimasmund and the Kum suite over there. So we seem to have a spatial distribution of cumulate rocks to the west, and less cumulative rocks to the east. If we, and then this also comes out, this difference here also stands out in the incompatible elements, where it's exclusively, of course, we have fewer samples here, but it's exclusively TBC samples that have this low abundance of incompatible elements, which is typical for cumulate rocks, whereas all others ones, the Kum and the Kaimasmund, are magmatic non-cumulates. And we could also try to bring back the structure here, and if we have this dextral displacement, that actually brings these 4 complexes closer to each other. So we could be talking about a greater Kum complex if it is. Now we're going to zoom in on the TBC that we've been working on. And here are some maps that were done earlier on, where most of them are consistent with an ultramafic body down to the southeast. And then rest of it is gabbroic rocks that are more or less altered, where the dark green rocks are the fresher rock, and the more sort of blue-green colors are altered rocks. And that gave us the first working hypothesis that this was a tilted layered intrusion, where you have the ultramafic base at the base, and then you go up to more differentiated compositions. However, our fieldwork here has sort of indicated that this gabbroic keep on looking up there. These gabbroic rocks, they accumulate very distinctly, but they're truncated by something that is cutting it here. So we might be dealing with a second intrusion or two intrusions in this. And this is actually supported by, use these ones. This is supported by a new discovery of some troctolites or melatroctolites that actually grade up to becoming dunites. The olivine, you can see there's two transects here, sample transects, one to the west and one to the east. And from the base and up, you can see that the olivine or the color index increases as you move up, and this is mainly olivines, whereas you have plagioclase. And this whole sequence is capped by an anorthosite. And if you think about the modal variation here, it could be very much like a reversed. It could be going the other way, you would think. But basically, we have indications from mineral chemistry, very preliminary, the top and the bottom sample, which indicate that the forsterite number decreases upwards. This is partly supported by anorthite number, which also decreases and along the eastern traverse, although in the western traverse it's opposite. But I think we have an upward stratigraphy here, and this could be the base of this second intrusion, which would then differentiate into gabbroic rocks up to the as indicated on that arrow there. However, we can also consider that these ultramafic or melatroctolitic units that we have are actually independent units, because we will see as we move into the key area where most of the research, the main ultramafic unit here, well, then we have made some transects across this. It's indicated here, some sample transects, and we look at the thin sections of these. We find that to the west, in the sort of purplish color, we mainly or exclusively have olivine cumulates, and I use the cumulate minerals to classify the rocks here. So we call them dunitic in that sense. And then to the east, in the sort of paler or cyan colors, we have, I'm going too fast here, sorry. So basically we have olivine cumulates here, sort of schematically illustrated here. And then you have, even though you do have intercumulus phases like plagioclase and often orthopyroxenes, which then reacts with olivines, reducing the amount of olivines, we still classify them as dunites. Just to reveal, keep it simple, because if you include the intercumulus phases, it gets you can get lots of different rock types. But if you go to this east of this ultramafics, we find that we have actually cumulus orthopyroxenes together with olivine. So there we have more of a Harzbergite. Then there are troctolites on either end, but this is the main sequence there. And if we think about these sequences, we often have Harzbergites and dunites and Harzbergite sequence, cyclic units in many ultramafic parts of the late intrusions. So we could interpret this, because remember, we thought that the differentiation was going towards the northwest. Well, we could then have a top of a cycle 1 here, which was then overlain by the base, a dunitic base of cycle 2. However, the mineral chemistry along these transects seem to indicate that we actually get a decrease in the forsterite numbers here, as well as the magnesium numbers of the orthopyroxenes or enstatites and the chromites. All seem to suggest that the differentiation is actually in the opposite direction, which is of course consistent with a dunite overlain by a Harzbergite. But it gives a problem, because now the magma chamber for this ultramafic unit is very, very small. But we'll come back to that. There was been drilling in the 1970s in this area, and they were exploring for nickel-copper deposits there. They found some anomalies, and they made some very shallow vertical drilling grid here. And they did discover some mineralizations up to a percentage of nickel and 0.38% of copper, but not enough at that time, and probably still not enough to do any mining or go any further with this. The drill core from these, or the core samples, were discarded on their camp nearby. And from these, we actually selected some samples and we picked out the mineralized samples, the sulfide mineralized samples, and in particular some orthoperoxenite samples, with very quite well preserved, as you can see in this image here, and mineralized. Since these are orthoperoxenites, and we have this stratigraphy from dunites to hartsbergites here, and these drill cores are vertically, well, and the orthoperoxenites only come in this area here, well, that should indicate that we actually have a dipping of a stratigraphy towards the northwest. It's the only way that the drill cores can intersect these hartsbergite or these orthoperoxenite bearing samples that we have here. However, if that's the case and the structural height is towards, or the differentiation is towards the southeast, that would indicate that the stratigraphy was overturned. All right. So this is where we get into Daniel Ferreira's main work here. He's investigated these sulfide mineralization. And here's a CTX scan of these, 3D shot here and another normal shot here, where you can see that the sulfides are mainly restricted or concentrated in the interstitial places in between these orthoperoxene cumulus grains, which is not surprising, which is very typical. Oh yeah, we do have some brighter specks in these scans here, which indicate some higher density minerals. But before we get to those, we'll just look at some reflective microscopy, which tells us that we are dealing with primary chalcopyrite and pentlandites and pyrotites in these samples. And this is, seems very primary and formed during the crystallization of these rocks interstitially. And they are partly variably replaced by secondary pyrites, as well as a second generation of granuloblastic pyrotites. In addition to that, we have these more exotic hessites or silver tellurites and electrums, as well as PGMs. Well, I'm going to list here various types made of platinum, palladium, tellurium, and bismuth, as well as one with tin. And these are, of course, if we look at the electron backscatter image here, these are the ones that give up the bright, dense or high density brightness in the previous core sample that we saw. And here's an example of how these PGE minerals are hosted inside this silver telluride. We sent some samples to Australia where Dr. Laura Martin analyzed these for sulfur isotopes, and these are the results we have here in delta 33 and 34 sulfur, and they are all lying within mantle values, as well as lying along this mass-dependent fractionation line, which tells us that we don't have any Archean sulfur involvement or any involvement of any the great oxidation event, basically. And it's not surprising because this is a mesoproterozoic orogeny and very few Archean rocks in this area. But then, it's getting time. Okay, I'll try and rush it up. Then we looked at the sulfur selenium ratios, and the fresh samples lie here. They are on the mantle array, and then there is a desulfurization due to more alteration. It moves to that side, but no samples are inside the more enriched ratios. So there's no externally derived sulfur from this area. And some other process of calcification must have given this mineralization. R factor values are 3,000 around, and basically a little bit more towards a PGE than a massive nickel copper deposits. And if we compare it to these two types of deposits and the precious metal patterns that they have here for pentlandite and pyrrhotite, is again straddling these both types of mineralizations more or less into one or the other. And overall comparisons with different characteristics of in different deposit classes also makes a greater similarities with PGE deposits. So we must have some kind of a nickel copper PGE deposit here, which is typical for post Columbia, you could say, or post Bushveld that we typically have. But the size, of course, is probably not in these world-class giant or super giant classes here. But and that very much depends on what size, what magma, how much volume of magma chamber was there for this deposit. It could be as small as this one here. If we have a structural height there, which would be a very little mass of magma to scavenge for your precious metals, or it could be half of this or the whole of the TVC, or it could even be the entire greater Cum suite. Sorry for going a little bit over time, but